All right, thanks, Max. Yeah, sorry, everyone. I'm not sure why was happening, but you started very late, and thank you for waiting 20 minutes. That's something. So what's the story? These three lovely people, including Max in the middle, they've been a part of this work. The lady here at the right, her name is Karen Connor. You guys may know who's she. I don't know if she's on the line, but she has expertise in structural geology and tectonics, and she's been very she's been working a lot on all her career, but recently in Mount Isa for interpretation of geophysical and geoscience data sets. And she's interested in basically making geological model using geophysics. And of course, if you're looking at deep geology, one of the things could be empty that could help you. And she found this paper last year from Max that was on joint inversion on Ernest-Henry. And she sent me and two other geophysicists an email that I'm sure you've seen this. It's very interesting. And we're like, oh no, neither of us actually have seen it before. And the other two geophysicists, one of them was Janelle and another person. And so, you know, I kind of got interested. I started looking at the paper. And basically, what Max has done, if this little map here shows where the survey area or Ernest-Henry is. And there are these little dots here over gravity data that they show the empty stations. And he has done joint inversion of empty and gravity using GIF3D, which is a joint inversion framework that he has, I guess he's the owner of it, or I don't know, I looked and I saw, Max, you can correct me, but many people has listed as developers, so I'm not sure how it works. And yes, so the interesting part for us about this joint inversion, or for me, was that when you look at these two models, comparing the bottom ones are the ones that are individual inversions, and this one is density, this one is resistivity. And when you look at the joint inversion, the resistivity, for example, has a lot better structures, and the structures are a lot sharper at the boundaries comparing with the individual inversion of the resistivity. And with density is the same thing, I guess. You can see that there are more structures, although with individual inversion of density, you really don't see any kind of those structures. So seeing these structures in, you know, in resistivity inversions kind of gets sharper, and you can see the boundaries better. It's kind of, I think, very important, because always with resistivity inversion, doesn't matter what you really, as a DC resistivity, like you're using IP or is that you're using MT, there's always this blobbiness with the inversion that you always see, and they just kind of, it's the nature of it, that it fades away, your resolution. And making that looks like this, to me, it's something, it's real improvement. And so we thought that this is, for what I will show you later, that could be interesting. So back again into, I guess, why Karen and Janelle, they are interested in this sort of inversion, is this basically project, it's just called Deep Crustal Seismic Interpretation Project, that Karen has been a part of it, and Janelle has been a part of it, and I'm not sure what maybe other people from GSQ. So there, in this map, it still kept those Ernest-Henry and the MT data that Max has used. But there are few seismic lines you can see here that has been a part of this project, and the aim is that they use the seismic gravity and MT data and to understand the larger scale structure underneath the Mount Isa. It has been a lot of work on this using MT, using gravity, but there were, and I guess the reason for it is kind of clear. This is some of the slides are from Janelle's work. I like this one because it shows that in this area we have a lot of cover in Mount Isa area, and if you look at this, basically this is the depth to basement, and this kind of this area that is surrounded by this black line is where you have the thinnest cover, and these are the minerals that they've been explored or occurrences of them that we know of. A lot of them are here and little outside and nothing really here. You go further south, the cover gets thicker. So the motivation of why you need to know this is kind of clear, and all of us probably, if you are familiar with the area, know that. And there, as I mentioned, there's a lot of work done around this, and if you're interested, you can use the this link here and look at the report of the seismic data and get the data or what has been true. So far I guess I talked about the why people are interested, but I personally, I'm interested in doing inversions. For me, was I felt it's a challenge, and I've always heard about joint inversions, so maybe I tried to do one, and it's a bit of an I guess it was a bit naive, and I can tell you why. Because technically there's, this is Ernest-Henry again, back to start, and Max's paper is on this data here, very neat at the top. The area that he has used for the inversion is 35 by 70 kilometer, and the spacing between those stations are 2 kilometers. And this is broadband MT, and the gravity data also, which is at the underneath in this map, is 2 kilometers spacing between the stations. So further south, I guess I showed in this. You see, this is I went back, but this is one of the seismic lines. It's called CF3, and this one is CF2, and so I'll show you later. But there are MT data along those some parts of this seismic data. So there was this seismic, this MT data along CF3 that Janelle is working at the moment on it, and we thought, we come and try to do joint inversion between gravity and MT for CF3, but I said naive because it I didn't say it because I just want to use the term. It was just really, if you look at this, it's actually quite challenging. The size of this line is 500 kilometers, and it's only just one profile. And the MT stations, they are apart from each other by 10 kilometers. The density of gravity data is very similar to what is at the top here, is 2 to 4 kilometers, and this one is also broadband. So I zoomed in a bit on Max's work. I guess if you look at it a bit closely, so because in the previous slide I show you a grid, and the grids are always of colored and nice, but when you go and look at the data for almost every gravity station with one MT and or maybe more, but the thing is, they're kind of, I think it's a very good data set to use for joint inversion. And I can tell you a bit more later that how this sort of things can, come together, basically the station spacing, for example, or yeah, other things that they are important. So the other thing I should have mentioned at the beginning, I guess the talk started so late, I forgot what I want to say at the beginning, but yeah, my talk might be a bit technical, I don't know, or yeah, there's a lot of detail about what I've done. I'm not sure if the people that they waited, they want to hear about that, but I hope that's what they want to hear. Is a bit about GIF3D, just joint inversion frame, basically the 3D joint inversion frame. The most important thing, I think, is an open source software, because a lot of things you have to pay for it, and that wouldn't be possible for me to, just run if I needed to pay. Max, I used this image at the background from your talk, and I'm sorry it's low quality, but I thought it was good because it summarizes what it goes in GIF3D. It works on Linux for if you were interested ever to use it. It can be run on a virtual machine locally on Windows. I mean, it depends also. There's a limitation, of course, with your memory. I'll tell you a bit more later, but you can do that. I think if you're looking at deposit scale, GravMag joint, it would be really easy to run it on a virtual machine on a Windows, no problem. So you can use for seismic, magnetotelluric, gravity, magnetics, electrical resistivity tomography, which is the DC resistivity, fancy word for DC resistivity, basically. There are different methods for basically what they, Max calls it coupling, or people call it coupling. With magnetotellurics and gravity, I think with the coupling, he uses mutual information. He's the one to ask question about this stuff. I'm not. But the other interesting thing about it is that you can have prior information, and you can put that in the model as a constraint. I haven't done that in this example, but apparently you can do that. And yes, you can run it on the clusters. Obviously, that was at the end I have to do. And I guess I had a conversation with Max about the machine learning part of it. That is obviously inversions are machine learning, and there's only a geophysical model there for machine to go towards it. So yeah, this is the only part that has a bit of a sort of looks like a bit of an equation. I thought it's important if people are interested to do this work or work with it. If you just look at it, like, what we always, they told us about inversion, a general inversion objective function would have a form of this. You have a misfit function for your data. You have your trade-off parameter, and then you would have basically your model function, and you're trying to minimize this to get the inversion going. This is for if you have, I guess, one data, but if you are looking at joint inversion, what Max has in his code, it's a bit more complicated. You have this objective function, and then you have misfit for empty, you have misfit for gravity. Then we put this term aside, you come here, there's regularization, you have it for empty, and you have it for gravity, and then each of them have a weighting function. And the middle one is the mutual information one, or the coupling one. That basically it's large if you have a say a variable that you have knowledge about it, say here you know about density, your resistivity, you know how much it is, and then how much then that variable can provide information for you on the other one. So that would be your mutual information. If it's high, it means it makes sense. The information you have from one can give you a constraint on the other one. I guess one is that physically they have to make sense. Those two parameters are you're looking at probably. But in the coming slide, I'll show how a little bit how it works. I'm keep moving this. I don't know where this is supposed to go. Max, where this is supposed to go. Yeah. Anyways, I will put it here. So what I did in this area, there's a lot of empty work that has been done in the past. But with gravity, it's not as such. One thing is, I guess, with gravity and magnetic, normally, I guess I'm not maybe eligible to say this, but I think regional inversions are not so. I haven't seen many like for at least this part of the world that you can go and see, download the regional inversion. I mean, people do a lot of deposit scale, but so I have to do the gravity and get a bit of information, do it at least somehow that what is good for the inversions, plus that I showed you how they can affect each other, the gravity and MT. So the area I started the gravity inversion by, I actually used another software for the start because it's called WinDisp, which is from Scientific Computing and Applications from Adelaide. Maybe some of you know the software. If you have any question, you can contact John Payne about it. My thinking was, I've done gravity inversions before, and I thought, my experience was you get this, symmetrical kind of, the line is in here. I go the top and bottom, kind of make it a neat rectangle. So, and it's a quite large area. There's already some of the problems I can see here and here and here with this grading, which can show it could be grading, but it could be data quality too. So I started with this, and I thought, I just do a few things with the software that I know, see what comes out of it, and I could compare it probably with what Max has done. And the first thing was that we decided that I have to remove the high frequency content. And the reason for that is, my empty line, I guess, I mean, even for, out of the joint inversion, if you would want to do such a big area for gravity, you would better off to remove the high frequency content, because you're capturing something much larger. You're capturing a lot of bigger structures, and that can produce a lot of blobbiness and noise in your inversion. I did try a few filters, 500, 1,000, 2,000, and the best one was 500. This inversion here, the cell size was 2,500 by 1,250 by 600, and which was the 500 one. And at the end was like, okay, this is a good start, with that cell size. And I guess this is observed data here. I should explain a bit more. And this is what is predicted. This is the Misfit, and this is the error percent, which is here is this bar. And it's the way I would interpret this. The green is 0, and this is supposedly, if it's more green, it means it's a better fit, and if it's not, it's red, and you can see blue. It kind of looks purple, but they are the two very high end of the errors. And with this one also, you just see those boundaries really, which is, I guess, always a bit like that with smooth inversion for gravity. You're averaging in your forward process, and then in the inversion you ask for, finding the boundaries. So that could be quite problematic anyways, because you're doing the opposite of what you did in forward. So it's just smooth inversion algorithms meant to do this. But so, okay, so far we've done the gravity. Also, the other thing with gravity inversion generally is that I think that in gravity inversion, the cell size matters. This is exactly same inversion for the area I showed you. I did it with WinDisk. And this one, that's just the only thing is the size along the X and Y are, this one is a coarser one. And what it tends to do is that it's kind of, there are a lot of striky sort of yellow that you see there along the X axis. And here also, instead of being kind of a round, they're all, they are striky, which is just the only difference between these two is that one of them has a bigger cell size. So with, I guess with gravity inversion, I would say the cell size, the shape of your survey, how big the area you're looking, what are the structures, it could affect your inversion. And also the quality of your data, obviously. Sometimes if you have, like with this software particularly, is you use the grids, and that can be a problem if you use a grid that there are, it has been done bad. It's actually, you see, if it's, for example, airborne magnetic, you always see the strikiness between the flight lines, for example. But Max's code uses actual numbers, which is, I think that's good. You can get the numbers in there. This one, you have to go with the grid, so you can get the data. You're using the product of someone else's work, and that's sometimes can be bad. Yes. So the next one is what happened, and from that inversion, what did we do? Okay, so for the joint inversion, I showed you what I did with the other software, but for some reason, I thought that was a brilliant idea. I'm not sure why. It has been a very long process, actually, I have to say. And for me, has been all new. So I went step by step, okay, let's do this, let's do that. I actually ended up using this dots that you see for the joint. And I guess for Max, probably it was very clear from first day that I have to keep it close to my MT. You probably now think, oh, okay, yeah, why would you use it? You didn't have any data for MT, it's supposed to be joint. When you get far from the line, I guess with MT, there is a bit of a, if you think of those hemispheres, there's a bit of a penetration on the side of the line, but how far that can go 100 kilometers. For you, it goes, I don't know, 2K or something. So yeah, that was the thing that I used for joint inversion, the dots. And one thing happened during running it, and that was one of the mistakes I made was I was trying to run this inversion just not as a joint in the same time that I was running the WinDisk, but I was trying to run it on Max's code, so to see what the gravity, because you could do it individually, would give me. I mean, what's comparable, what's not. And then like, I know that the sensitivity metrics can be large for gravity inversions, but then it just keeps going. I'm checking it, it's like it's running out of space almost. I mean, I'm running it and it's like almost a terabyte of sensitivity metrics. And the way it calculate, you can calculate it, or the way it works, the memory that you need is, so how many cells you have in each direction and how many data points you have. And then there is an 8 for storing those numbers. The float number, basically 8 byte. Is that 8 byte or 32? I don't know. One versus the other. 32 byte, 8 digit. Nah, I don't know. So there is an 8 there. I read, but I cannot still remember really. So at the end, like for this area, I was trying to produce something that was 1 terabyte. And one of the reasons was that I was using, I told you, I started using the grid. So I have the grid, and then I went back from grid to have the CSV for access code. So even they have 2 to 4 kilometer points on the map, when people grid, they may, they just grid it, 4 times more than what they've got data. And it was going for each point, each kilometer, or each 2 kilometer, I had 1 data point. And then I started reducing that. And I think Max, in his paper for Ernest-Henry, he has said that he has downsampled it to 500 meter or something. But yes, so at the beginning I said you can run it on a virtual machine, depending to the memories. This is just a simple thing, but you have to consider. If it's too large, I guess you're gonna run out of the memory, just simply. So I've got the joint, gravity sorted in terms of parameters. I'm showing here one slice, and one depth slice, basically, of the joint and standalone gravity inversion with GIF3D. These two, both of them have a same cell size. This one on this side left is the one that I ran. This was my very first model, one of my very first one, and it only did 20 iterations, and these are both at 5,000 meter or about 5K, and just stopped working. Didn't go further. This one was joined with MT, and it went much further, and the RMS was a bit better. The only thing I want to show you in this slide was, sorry, let's just go back. It's just, they're quite similar, but one is, well, I guess it did more inversion, so there's more, and the color stretch is same. But it was interesting to me because, I wouldn't think like, why would just the standalone gravity inversion didn't go far? There's nothing like, and I played with this stuff a bit GIF3D with I don't know, cell size or changing things, but it wouldn't produce much for me. With the joint, it seems I got a bit further, even in terms of gravity. Now go back. I'm gonna go back to the empty side of things. Tell you what's going on in MT. So because I said, there's information on MT. This is probably, you've seen it before. There's a lot of MT data in this area. The one that I'm using today and I'm showing you is this one. And Janelle has done some work on this, plus this MT data and some other, I guess, company-owned data is here for her. That she has used, and I will show you what she has achieved so far. This is where Max has done half of it, and I think the other half of it, is still working, and I think she showed it on her presentation on MTNet, the same series of seminars. And there are other models and inversion has been done here, and I can show you what basically is important in terms of, I guess, electrical resistivity, and then there is a bit of a result to show. At the beginning of my talk, I told you, we were interested in, I guess, structures and deep crustal structures in this area, and we have all these seismic lines that we were trying to interpret. I guess one thing, though I don't know much about geology of Queensland, I have to say, Janelle is probably the person to ask questions. But there are a couple of things people were interested, including Janelle and Karen, that one I think is this Giza structure that's in this image. You have a slice of 33 kilometer depth of a model that is done by Dawn et al. At 2020, and it's from Oslam. And that's basically this conductor, Kalankari conductor anomaly. That's where shows where the basically Giza structure is. Then there are two faults here that I guess they come and cross where I'm working. I think this is Pilgrim fault, and this is Yurandanji Borktown fault. The other thing here, I guess there is a central block that is resistive, and there is here conductor, and I guess this line shows where the data, Oslam data is. So one thing is this structure is important, I guess, geologically. And the other one are basically here, there's a few more faults that, people are interested in knowing how far they go and all those sort of things. With this one, again, this is from Janelle's presentation. These are the seismic line that I showed you earlier, and these are the empty work over them that they've been done by Zhang et al. In 2018, and they published. So with these models, again, what you can see is that basically the Giza structure, and what other thing that I have to mention here, I guess these models are from Zhang et al., but I guess Janelle has put some structures here. The seismic structures at the back, you can see how basically this conductivity here matches the Giza structure, and further south it gets a bit weaker. And the other thing is this one at the bottom is Janelle work that has been in progress over this line that I've been doing the joint inversion over that. Yeah, so these are the things that I knew, I guess. And this one also is similar. Again, same work, showing there is this structure here that is conductive. Is hoping that Giza structure would come out, and then there's a conductor here. They're showing some fluid path, but I guess in the next one, this one is probably the one that would be important to show in regard to the work I'm doing. This is the work that Janelle has been doing, and she's trying to publish it. It's in preparation, so she kindly given me this to put it here, and it's the same line basically. I guess if I go back here, is this one, and CF3 that I basically am working on. At the top is the forward modeling that she has done with the gravity. this is the seismic interpretation that has been done. And this is her new MT model that she's hoping to publish, which has changed a bit, I guess, from the previous preliminary one that was in the previous slide. But what I guess we were hoping to achieve with these inversions were this structure peta is underneath this sort of underneath these two folds, and here you can see a resistive structure. I guess kind of it should be resistive, but the eastern side of it, there is a conductor that's and also on further north you can follow it, and the basically other inversion that has been done. It's a bit of a, you know, it's a bit of a question. You would think either because you can see the you know, these reflectors, and you can see the, you know, the resistive here, but why you wouldn't have the same kind of a resistive area here? And it's, you have this conductor, and then you have the, here in the forward modeling of the gravity, you have a peak, and I think these are supposed to be a bit of a, in terms of conductivity contrast, actually, these ones, they don't have any conductivity contrast if you look at this color scheme here, but there is a bit here conductivity contrast between this and that. These are more conductive. Sorry, density. Pointing at to density. There's no density contrast here, but this is more dense, and you can see the peak. And if you come down here, there's you have this just, you know, conductor, and then you have a resistor here. So my main thing was if you could, you know, do a joint inversion basically, and you try to come up and improve maybe this model. The parameters at the end I use at the joint MT inversion. This was a bit I guess this is the biggest mesh I could use, kind of, I think 160 by 50 by 40. I think I'm not sure, but Max maybe can answer this one. I don't think at the moment it can handle bigger than 160. Actually, I'm not sure. He can correct me.
Do you want me to say something now?
Yeah, Max. Is that, what's the biggest mesh size you can handle in your code?
So you can do bigger. I think you asked me for a bigger size sort of executable, and I sent you this because it was still seemed like, you know, it can be run in a decent amount of time. Obviously, yeah. The bigger the mesh becomes, the longer things take. So, you know, and this is another discussion. You could go finer and bigger, but then it would just take, you know, let's say a week for a run, or maybe even longer.
I see. So there's no limit in the mesh size?
Oh, your computer memory and your time is
that's true. And yeah, I mean, it can go to coma basically. I guess I've seen that. If you're not right, picking your parameters right, it just you know, just doesn't do anything. Maybe for 10 hours it's just, you know, you've done a bad job and goes to coma. Yes, okay, so that's the cell size. The reason was probably want to get something out of it. Mesh size, and the cell size, I ended up using 3 kilometer by 3 kilometer and 500 meter along there. The starting model, I had a you know, I got lucky because Janelle has done inversions on this line. Otherwise, in such a short time, I got over gravity myself, but I couldn't really do it without their help. 33 ohm meter did, I don't know, some magic. We started with 100 ohm meter, and with 100 ohm meter, and you know, there's coupling. The coupling, we started, you know, from a million. That was the first one, and with 100 ohm meter, it did 100 inversions, and it was like, what is this? It just was like two things that you basically given it to a, you know, a painter, and they exactly were same, like it didn't do anything. And it was like, oh man, this is I don't know what I was supposed to do, but it was amazing. As soon as I changed that 100 ohm meter to 30 ohm meter, it started doing something. I guess one of the reason, I mean, we know that the starting model can be important for MT, not so much with DC resistivity. I haven't seen that. It's just a small data set. And you know, there's so many numbers here. The computer has to calculate when it's going to come from, you know, to an answer for that objective function. And you have 100 ohm meter and so many cells, and then you have coupling. So just it can't get over it. Like I said, at 100 in iterations. But yeah, I guess the 30 ohm meter was very helpful. Then the other problem we had, I mentioned that it's went to coma. There was a time that the frequencies that I was using, or the data file that I started using, was the same as the one that Janelle used for the inversion that I've shown you previously. And the reason was, I just, you know, I thought she's doing something. Let's see if we can compare it. And at some point, the frequencies that she was using, I used 0.25 to 630 seconds. She was using a lot of higher frequencies. And I grabbed that data and, you know, I started using same one. And one thing with GIF3D that is good is it actually shows you for each frequency how long it's taking to do an iteration. So at some point, it seemed that it was really struggling with those high frequencies. I had a chat with Max, and we had a look at the frequencies, and it's removing those. It just was like a magic. And the number of frequencies, they haven't been many, 18 frequencies, but I think you don't need basically to produce a model use 100 frequencies. We know that, but it was very, you know, it was very, very helpful to get those frequencies out of the way. It wasn't happening, and it wouldn't bring the RMS down, and you know, that was problematic really, and it was going to coma for, I don't know, 5 hours to do one iteration at some point. And I mean, at that point I knew this is strong, it shouldn't take that long. The other thing in this image, this is I guess they're at about 4,000 meters. This is gravity, and this is MT. These are depthless slices, and this what I want to show is just the importance of the coupling. The coupling for this one, which was the final model, was 100,000. We reduced it because with coupling, if it's, you can see here, right? With gravity, you have all these structures, and I guess you have data for gravity here. For MT, you have only this line, but it starts producing similar things. Does have data or not, that's what it tries to do. And I guess as a user, you try to control that, and coupling factor, it's basically one of the things that you can do. But if you have it too high, it's kind of, it's going to be really similar. It's going to be, it's going to look really, really weird, and almost feels like, why did I do this? Like this is exactly the same thing. And if it's low, it starts, they don't look like at all. Like if I tested this with 100,000, and it was like two separate things, and it was also weird. So there is a point that you should, you know, test this and I guess get it right. And that's probably why it takes a bit of a time to do this. And the Misfit that I achieved with the joint inversion, actually, it wasn't bad. I'll show you a bit of result in, I'm going to show in Geoscience Analyst, because I had a hard time to bring them in. I'll tell you that. But that's, I thought that maybe I'll show the Misfit first, because I guess you want to validate a bit the result. But yeah, with the gravity was about 9 something, and with the MT, I guess at the end was 2.34, which was pretty good. And the roughness, I guess it has increased for both of them, but it kind of got plateau after, maybe, I guess after some point, which is good, because I guess it's started to produce the structures that we want, but it didn't make it like super rough, which that's good. And yet, I'm gonna just do this and show you. I just put this in here because if there would be a PDF, I just want to know that there was something I showed you guys. So this, let me just maybe turn off the. So this is the empty line. This is from top. So my mesh was around this, right? So if I would have
Sasha?
any, sorry?
I think we're still looking at the PowerPoint. I think you meant you have to share a different window because you just shared the
Yeah,
window.
I knew that. Remember, I said, I don't know which one do I share. That's what exactly I meant. Share, because it's tricky. There is one, if you pick that, it shows everything.
There's the desktop.
Find that one. Yeah, thanks. So, okay, yes. So this is showing you in Geoscience Analyst, and I'm just saying why I couldn't bring it in, because the mesh around this is like that, right? I'm showing you from top, and my slice is basically, because this is a profile, it was quite hard to if I would show you any slides. I haven't figured it out, and admittedly this was running till 10 a.m. this morning, so that's why it didn't look good if I had this, like, one slides with 2 points, and I showed you, I mean, that coupling slides, that it gives you, inversion gives you always something. Can be a Mickey Mouse, for example, in terms of potential fields. Yes, so that's the MT station. These are the faults, and I attempted to cut some of them, but I was unsuccessful. This is the area that I showed you, and I did some gravity immersions over it and make it smaller and smaller. The faults, I think that I showed you earlier, they probably are, this is your Ndanji Borktown, and this is Pilgrim Fault, and I think this is Black Mountain. And yes, the seismic lines, let me just move this one. There is also, I'm gonna show you where the seismic lines are. Yeah, so this is basically maybe back to MT station. This is the seismic interpretation that you've been saying, and yes, I was hoping would be a bit this, like along this. I'm not sure why it's like that, but I guess Karen, I got it from Karen. She knows why it's like that. So I remove this one. So yep, that's the Pita, I guess zone. That's and the faults. I guess I remember I told you there would be a bit of a conductor here, apparently going on along other lines along north, and there's an effector. And what I actually got from this is a bit different from what Janelle has done, and I am still not sure. This is the model, one of the slices. So if I maybe I had a panel to where's my panels, colors, data colors, yeah, maybe, yeah. Yeah, sorry, just trying to. Yeah, I can't. It's funny because I work with this all the time, and now I can't make it to my visual parameters. Yeah, that's when you talk. Yeah, just maybe make it a little bit transparent. I know it sounds a bit, looks like a bit funny, but yeah, I guess with this one, I can see the folds here. That one is looking this way, which is, I think, that's a black mountain. And these two faults, one of them should be the Pilgrim Fault, I think. So this shows those where they are located. In terms of the conductor that we see, I guess I'm not so sure if it's happening exactly here. I kind of see this looks like the top of the Pita Pita. Then I have another one that I caught, and I thought these were the ones that they were just making sense to me, but you know, not from what I was hoping that I achieve. And this is again from this side. If you look, looks like the Pita Pita. Yes. One thing I want to mention here. Well, I guess this is just finished. As I told you, this was really new, and I am actually my concern. I like to publish this work at some point, I guess, but with showing this, I guess, and the RMS is good. The gravity I didn't show. It's just it's really I haven't found a way really show them well. I said it wasn't making sense. The slices when I was cut, I didn't know how to do what I've done with MT. It actually was a bit of a work to make this happen here. But one thing is, I don't know, is that because of the frequencies? Actually, I'm seeing something like kind of a more clear, because I guess with Pita, if I go back to, I guess I have to stop and I guess, shit, I'm very clever, aren't I? Oh my goodness. With Janelle's work, it's kind of, you can, when you look at it, mine was like more, this is more conductor kind of underneath here, and then you would have the resistive. I don't know, is that because of the frequencies? Is that, still, I'm not sure, to be honest myself. Like what I saw here is that, you know, because I removed the lower frequencies, and the range of frequencies I used in the south, I've done, or maybe in the somewhere, I've done some inversions of MT 2D, and the structures, you could really, the same faults, you could see them between 0.1 second to like 1,000 second, but that, or maybe less, nah. But there was this range of frequency that you could see the fault really clearly. And I don't know if, because with the inversions, with, as I mentioned at the beginning, it's really that content, and in MT comes with the frequency. It's that was giving us hard time at the beginning and going to coma. And with gravity's size, cell size, mesh size, and yeah, so these are the things that I like to do. I guess I like to. Also, I had a chat with Max. So there's an uncertainty of it, but it's the model. I mean, the RMS is good, but yeah, I need to work to see a bit if the result, you know, I can validate it somehow a bit further than RMS and Misfit as one thing. The other thing, this code can actually get this structure, and, you know, kind of, you can constrain it with the reflectors, where they are located and all that. It seems what I showed you, that top bit also, I guess I forgot to mention, but the resistive was, this is 8, was at the top, was 8 kilometer. So yeah, that's about it, I guess, for me. And I'll stop sharing. And yeah, thanks everybody. I'm impressed that you guys waited that long for my talk. Thank you. And if you have questions, ask Mask. If you have any question, ask him.
No. So, well, first of all,
yes.
Thank you very much for that. I mean, certainly for me, it was very interesting to hear your perspective from somebody who's, using this code, because obviously it's a very different experience from, me having worked on this for a few years. And maybe just a bit of background. I mean, we've worked on this together, but I haven't seen your presentation. So, if I ask a few questions, it's not,
no, sure.
Pretend. It's sort of generally sort of that
Genuine
I'm
question.
curious. And I also just looked back, while you were talking, I was looking at our email exchange, and I think you started sort of working on this seriously in January this year. So five months ago. And certainly, I mean, having worked with other people, and I suppose your talk reflected this, is sort of I think you've now reached the stage where you're like, a confident user of the code, yes. And I think that's not unusual that it takes a few months, right, to put everything together. And in the beginning, it can be quite overwhelming, all these different, and you talked about that, all these different moving pieces and how they
it's different from
together,
just
right?
a standalone inversion of one thing. I think it's different, definitely. It's harder to find if something is wrong, I guess, where you're making mistake.
Yes, because you have all these sort of influences,
hard to guess,
that you need to take care of. I mean, I want to leave room for other people to ask questions. So let's see. Okay, while we're waiting, while people are still typing, so I think one thing you said very nicely is this thing about, okay, there's this coupling, yes, and this coupling sort of creates a similarity, yes, but it's sort of up to the user, or you as a sort of scientist to decide, okay, this is too much, this is not enough, and this is just the right amount. I mean,
I think you really need to know your maybe geology. That's the only thing. I mean, you can produce something at it. I'm sure you can. I mean, you can even have a good RMS maybe, but
I mean, so what was your sort of guiding principle so far to decide, okay, I like this one, and you said, okay, there was one, that you didn't like at all. Sort of, what about it was it that you?
They can be too similar, or they can be totally unrelated. It's very, very interesting. There's this place that you can probably see. It is making sense. It's a bit of a judgment call, like.
Yes, absolutely. I mean, at the end of the day, especially, well, both with this, what you're using, this variation of information constraint, but also what other people are using, or what I used previously, the so-called cross gradient, which is a sort of a different way. At the end, it's just maths, right? It's not geology. It's not earth physics. It's just a mathematical connection between the properties.
But works. It's interesting that I think it does work.
Well, yeah, but
it's cool.
I think, as you said correctly, yes, you need to instill the geological knowledge that you have as a person and as a sort of experienced scientist into the whole process, where you say, right, this one might have the better coupling number, but I know that this cannot be, yes, and then you modify, or you change your outcome. I mean, we still have a few people here, but it seems like, I don't know, either nobody dares to ask anything or everything was clear. No, I thought it was a very, from my perspective, certainly a very
There's one
is there a
Q&A.
question now? Oh, yep. Okay, good. So I'll read it and then you can answer. Thank you for your nice presentation. How the depth of the two geophysical methods controlled to make the joint inversion? Do they have the same resolution in each method?
I guess how they with the depths, removing those high frequency with empty and kind of filtering the gravity, that's what depths is kind of, we control the what signal defines the depth for us. Obviously it's an interesting question, because I think with gravity inversions, you really with potential film method, the depth is not something that you can really work out. I mean, there is that intrinsic problem. But in terms of resolution, I actually don't know. I think with MT, you can go far in terms of depth, and maybe it can. The same. The very first slide that I showed, that was Max's work. I said, you can see empty structures. The structures exist in empty, and with the joint, it's like it's better now. But with gravity, there's this thing. I don't know. Gravity not going to show you 100 kilometers. It's impossible, right? And it doesn't matter you use empty or not. It's very little you can see with potential fields. Yeah, the thing our thing that works, the way it works is wherever there is a resolution, because inversion is, this whole thing is inversion, right? The algorithm starts calculating things from a top cell and goes down, right? So wherever there is a resolution and these are helping each other, you get a closer fit, and that helps the whole inversion just get a better outcome. Otherwise, it's not that, you would think, oh, gravity would never give any depths like empty. But yeah, I think that way, maybe you have to think it that way.
Yeah, and just I agree. The way I think about it, but it hasn't been sort of proven yet, is that the MT provides a lot of the depth stuff, because, as you said, the gravity has trouble with that. But then, especially if you have relatively densely sampled gravity compared to the MT, it provides a bit more horizontal sort of. The fall needs to be in this location and not a kilometer to the right or a kilometer to the left.
Oh yeah, that's a good point, actually, because I think with MT that's a bit of a problem.
Sometimes
I've seen that sometimes with the faults, you just exactly don't get it where there has to be. It depends, right? What are we talking about? It's all the spatial resolution. If your sites are really far apart in MT, which sometimes are, yeah, I think the faults can be a little bit not in the right location, little bit, and that little bit is actually quite important. Yeah, so it can be fixed, I guess, with maybe putting gravity in there.
Yeah. And maybe I just remembered sort of one comment or one thing you said in the beginning, sort of about the difficulties of the whole survey setup. And I mean, one of the reasons I chose the Cloncurry survey was, well, okay, I had worked with the MT before, just to see what I can get out of this. But yes, it's a much easier setup because everything is nice and compact and square, and you picked something sort of actually quite hard with a single line that makes everything very big, as you need a big inversion domain. And I mean, it's possible to do joint inversion, and you show that it can produce value, but it's not the ideal setup. The concurrent, you know, geometry is much more.
It has to be a 3D.
ideal.
I think a 3D survey really would work. A 3D, like you know, like a, sorry, what do we call it? Mine was a profile. Yours was an array.
Yeah, more array shape, or you have sort of fairly homogeneous sort of spatial coverage.
Yeah.
I mean, for any inversion, right? I mean, you know, also a pure MT 3D inversion of that single line, yes,
would be hard.
It's hard, yes. You can do it, and you know, I think Janelle that's what Janelle is doing, right? But
it's interesting because what would be then if you have one line or lines profiles and they have a lot of 3D in them, what would you do? Like you'd see a lot of 3D frequencies. Like,
well, I mean, I skipped basically 2D in my education. I did 1D for a while, and then I went straight to 3D. So for me, I always go to 3D. But that's simply
good enough for you, Max.
Really gotten into the whole sort of 2D, you know, strike analysis. Workflow. But yeah, I think that's still, of course, an application.
That can be a problem. It's interesting that you say that. Yeah.
Well, it seems that we have sort of reached sort of an end. I just, you know, for those of you who are still there now that we, you know, are doing reasonably well on time, I just wanted to show you the next ones, the last two for this month. Yes, so next week we have Christine Chesley talking about seamounts and slow slips. So marine EM, and then on the 22nd we have Kate Brandt, so more from Australia, MT for lithospheric architecture and mineral systems in Southern Australia. So I suppose, you know, a very similar kind of questions and ideas that she will be asking. And then finally, on the 29th of June, there is the open mic. So if you have things that you think should be discussed, then please send us an email. So yeah, thank you again, Sasha.
No worries. Thank you, Max.
And yeah, hope to see more of this in the future.
Yes. All right. Talk to you soon. Thanks, everybody.
And thanks, everybody, for coming and waiting.
Thank you. Yes, certainly. Thanks for waiting. All right. Thanks. See you. Bye.